Assalamualaikum and salam sejahtera. So for this video, I would like to explain the continuity of the function. Okay, so we already learned how to compute. Okay, limit at a point and also limit at infinity. Okay, limit at a point and also limit at infinity, and several techniques. Okay, we have discussed several techniques on how to compute uh, uh, these two types of limit. Okay, so for now, so I will like also we have um, learn how to compute the limits using L'Hopital rules. Okay, the continuity, okay, of a function. Okay, so is the last section in this chapter limits and continuity. Okay, if we need to determine whether the function is continuous or not. But before we proceed to the definition of the continuity, we look at the several introduction to continuity. Okay, the path of a moving object. Let's say we have the path of a moving object can be perceived as an unbroken curve without gaps, breaks, or holes. Okay, in this section, in this section continuity, we translate the unbroken curve, okay, into a precise mathematical formulation called continuity. That is the continuity, the uh, informal introduction to the continuity. Now, let's say we have a function f(x) is said to be continuous at x equal a if limit x approaches a of f(x) equal fa, provided that the limit at x when x approaches a f(x) exists and the function of a is defined. Okay, so if the function satisfies this condition, therefore we said that the function is continuous. Okay, from this condition, three condition. The first one is the limit x approaches a f(x). Okay, we need to find the this limit first. Okay, then this limit must be exist. So when this limit is exist, we have the value L. Okay, let's say L. So the second that we need to check is whether the function is defined at x equal a. So we need to find the fa. The substitute the value of a into the given function. Into the function that we need to know whether the function is continuous or not. So fa. Then let's say the limit, the value of the limit is L1, and now the value of the function is L2. Okay, the function is defined and has value L2. So for the limit to be for the limit to be continuous at x equal a, L1, okay, so the limit x approaches a f(x), okay, must equal to fa. Okay, that means, okay, our value of L1 must equal to L2. Okay, this is the three things that we need to find. So the first one is the limit, the second one is the function at a point, and finally we have to check whether the limit equal to the function. Okay, Uh, we also we already know how the function is continuous. Then sometimes, okay, we can check whether the when the function has discontinuity. Okay, if the conditions of continuity fail to hold, then fx is said to has a discontinuity at x equal a. Okay, there are several types of discontinuity. This discontinuity we can check uh, by looking at the function. Okay, when the function uh, can be defined at certain point and cannot be defined at certain point, and when the limit of a function does not exist. Okay, that two conditions um, will lead to the discontinuity of a function at a certain point. Okay, there are several types of discontinuity. Okay, the first one is removable discontinuity. Okay, if we look at the graph here, okay, the removable discontinuity, okay, we have the graph like this. Okay, and at x equal x naught, okay, there is a hole, okay, at x equal x naught. Okay, if we look at this graph is supposed continuous. However, there's exists a hole at one point. So the removable discontinuity occur when limit x approaches x naught fx not equal to fx naught. Okay, because of the hole. The second type of discontinuity is jump discontinuity. If we look at the graph, okay, it's obviously that the graph has jump, okay, at x equal x naught. Okay, this is the obvious discontinuity of a function. So the jump discontinuity occur when limit x approaches x naught from the left hand side for the function not equal to limit x approaches x naught from the right hand side. Okay. The third type of discontinuity is infinite discontinuity. So let's say we have this for the example the graph at x equal a. Okay, the graph this type of discontinuity occur when limit x approaches x naught a certain point. Okay, or limit x approaches x naught from the right or left hand side approaches positive or negative infinity. Okay, this at a point a here or a point x naught, the function has the limit of the function approach positive infinity on the right hand side. From this example, from this graph, so from the left hand side the limit approaches negative infinity. So this kind of, we know that the limit that has infinite limit is does not exist. That's why, okay, the infinite limit when we has when the function has infinite limit, so we call it infinite discontinuity. Okay, the fourth type of discontinuity is oscillatory discontinuity. Okay, this graph, if we look at the graph example, the example from the graph, so the function oscillate, okay, at the x-axis, okay, the oscillate, and uh, this type of discontinuity occur when the function oscillate infinitely as it approaches a certain point. Okay, without setting on a single value. Okay, the limit does not approach any single value. That's why this when we have when the function has oscillate infinitely, when the function oscillate infinitely, then we call that function has oscillatory discontinuity. Okay, the example of the function with the oscillatory discontinuity is sine x, cosine x. Okay, we look at the example of continuity and also the discontinuity. Okay, continuity. So, for this example, so we need to determine whether the function below are continuous or not at the given point. Okay. If we look at the example A, okay, the example A, we have this type of function. This is actually the simple function. Okay, we know that from the example A. Okay, so we want to know whether this function is continuous or not at x equal 1. We know that the continuity, the condition for the function is continuous is at x equal a. Okay, continuous at x equal a. So limit as x approaches a for the fx, okay, must be equal to fa. Okay, so for the example a, so we need to find the limit. Okay, now x approaches 1. Okay, fx is 7x minus 3, set 3. Yeah. Okay, so 7 minus 3, we just calculate. Calculate. Okay, this is 5.268. Okay. You can write your answer into decimal places or 4 decimal places. Okay. Or you also can write your answer as 7 minus 3. So this one is never mind because we know that this function has a value at limit has this value at limit approaching 1. Okay, now, okay, so limit, we have the limit. So now we need to find the f1. F1 means that the function at x equal 1. So just substitute 1 into the function. We also get the answer is 7 minus 3. So say for the 7 minus 3 is 5.268. Okay. Therefore, okay, no. Okay, since the limit for x approaching 1, fx, okay, fx now is 7x plus, no, you can write down the function or you can just write the fx, okay, equal f1. Therefore, the limit is continuous at x equal 1. We need to clarify the point where the function is continuous because sometimes the function is continuous at for example x equal 1, but maybe, okay, the function does not continuous at the other point. Okay, so now we look at the example b. Okay, for the example B, okay, we have the piecewise function. So without sketching the graph of the function, so we can check, okay, whether the function is continuous or not at at certain point. Okay, so for example, we have this point at x equal 1. We need to check whether the function is continuous or not at x equal 1. Okay, from this function, okay, if I don't want to sketch the graph, but I just want to mark the not the graph, mark the x-axis. Okay, let's say we have x equal 1 here. Okay, when when x less than 1, okay, the function is 3x plus 2. Okay, less than 1. So let's say here is 0. Okay, for the function x greater than 1, say we have the function x squared minus 1. But when x equal 1, the function is 1. Yeah, the function is 1 when x equal 1. So, previously we learned how to determine the limit of the piecewise function. Okay, for the limit of the piecewise function, if the function has a different function at a certain point. Okay, for example, but in this example, at x equal 1. So if we want to know the limit at that point, so we need to find the limit from the left and right hand side. Okay, for this example, so for the continuity, remember that we need to find the limit at the particular point and the function, and also the function. So for this example, we need to find the limit, okay, at x approaching 1 for the fx. However, okay, for this limit, because at x equal 1, okay, we have two functions. Okay, therefore we need to find the limit at as x approaching 1 from the left, okay, left hand side for the fx, and also we need to find the limit, okay, for the function of limit x approaches 1 from the right hand side of x. Okay, for this limit, this is not equal. Okay, this one we need to find the limit from the left and right hand side. So for the limit from left hand side, okay, we have the function x less than 1. When x less than 1, the function is 3x plus 2. Okay, so just substitute the value of 1. So the limit is 5. Okay, from the right hand side, so we have the limit x approaching 1 from the right hand side, left hand side. From the right hand side, so we use the function when x greater than 1. So when x greater than 1, the function is x squared minus 1. So we will substitute the value of 1, so the function is 0. Okay? Okay. Okay. Now, what happened to the limit? So, because the limit, okay, here, from the left hand side and the right hand side, the left hand side not equal to the right hand side. Therefore, we said that limit x approaches 1, fx does not exist. Okay. Therefore, okay, therefore, the fx does not continuous. Okay. At x equal 1. Okay. Why? Because of the limit. If you sketch the graph, okay, let us try sketching the graph. So let's say 1 here. So when x equal 1, so we have 5 here. 5. When x equals 0, we have 2. Okay. So this function. Okay. So when x equal greater than 1, so when x is greater than 1, so we have at 0, negative 1. When x is 1, this one is 0. When x is 2. So I think the graph is like this. But since it start at the graph is like this. Okay, graph, the quadratic graph. However, since we start at the 1, so the graph from 1 is like this, the quadratic graph. Okay. Okay. Then when x, because this is not include the value of 1, so we put a hole here and also here a hole here. And when x equal 1, the value is 1. So let's say the value is 1 here. Okay. The graph is like this. So this is the jump discontinuity, removable and jump discontinuity. But obviously, this is jump discontinuity. Yeah. Okay, we can check through graph. Okay. For example C. Example C also the piecewise function, but this time the piecewise function contain the trigonometric function sin x. Okay, so be careful about the limit of the trigonometric function. Okay, for this kind of function, we don't want to sketch the graph. It's quite difficult to sketch the sin x over x. So now we look at the graph. Let's say 0 here. Okay, this is x. The end point, the end of interval, apa tu? The end point of the interval is 0. Here for this question is at 0. So if we look at the graph, okay, the function at 0 is 0. Okay, 0 is 0. However, when the function is not 0, okay, so the function is now sin x over x. That means from the left hand side, sin x over x, as long as the value is not 0. So from the right hand side also sin x over x. Okay. Okay. Now we need to find the limit. Okay, the limit as x approaches 0 for the fx. Okay, why approaches 0? Because we look at the question. If the question need you to determine the uh, continuity at x equal 1, so just find the limit at x approaches 1. So now we need to determine the continuity of the function at 0. So we need to find the limit approaches 0. Fx equal, okay. We don't have to find the limit for the for the left and right hand side. We just can find the limit from the two-sided limit from both sides. Why? Because from the left hand side and the right hand side we have the same functions. Okay, so limit x approaches 0 for the fx. Now we use the function sine x over x. If we substitute the sine x over x, of course we get the 0 over 0. However, so you back to the limit of the at a point for the trigonometric function. Okay, there they have the basic form of limit x approaches 0 for sine x over x. This one is equal 1. Okay, so the function is 1. Then the second one is we need to find, since the limit is exists. Okay, then we need to find the f at x equal. Now, if the limit does not exist, okay, for example, the question B, so we don't have to find the f1, okay, because the limit already uh, does not, the limit does not satisfy the condition for the continuity. So we can directly say that the function does not continuous. Okay, for this example, okay, the limit at x approaches 0 is exists. So but apa ni, the value is 1. So for the second, then we need to find the f0. Okay, so we need to find for the f at x equals 0. So we just look at the function. When x equals 0, the function is 0. Okay, for this problem, for this function, okay, since this is not equal, these two is not equal, but not equal. Okay, since limit x approaches 0 fx, okay, not equal to f0, therefore the limit does not continuous. Where x equal 0. Okay, like that. Alright, so we have looked 3 examples. So now for the next problem, so find the discontinuities of the given function. Okay, we know that the discontinuity occur when the limit does not continuous. So the limit does not continuous when the function does not satisfies the condition for the continuity. Okay, so you need to remember that. So for the first one, find the discontinuities of the given function. Okay, for the first function, we have the fx equal to 2 over x. So if we look at the function, So the function is undefined when x equal 0. Okay. Why? Because when x equals 0, the function is 2 divided by 0. Okay. So this is the obvious calculation. So if we talk about the limit, also the limit of a function of fx, when x approaching, remember that the limit of fx for this kind of function we need to find from the left hand side. The limit is does not exist. Why? Because the limit of fx from the left hand side, okay, is okay. This function is like this. We can remember the graph. Okay, the graph is the parabola. Okay, parabolic graph. Okay, and not parabolic, the hyperbolic graph. Okay, so limit x approaching 0 from the left hand side of x. If we look at the here 0, the 0 is here. So this is x, this is fx. So when x approaches 0, okay, from the left hand side is negative infinity. Okay, same as if we look at the limit x approaching 0 from the right hand side fx. So if we check from the right hand side, it's positive infinity, since this one the left approaching 0 negative infinity, the right approaching positive infinity, then the limit x approaching 0 for the fx does not exist. Okay, if we want to check the limit, okay, if not, you just use this condition, because the f0 not equal to this is the undefined. So this condition is enough, okay, to clarify that the function is not does not continuous, has discontinuity at a certain point, does not continuous. Okay, this is the explanation, but how to answer this? Okay, find the discontinuity. We want the discontinuity. Okay, the fx has discontinuity. At x equal 0. Okay, for the other point, I don't think there are any problem. So for the x equals 0, why? Because of these two conditions. Okay, so the first one is f0 is undefined. The second one, if we check the limit, okay, the limit does not exist. Because why? Because for the function to be continuous, okay, the function must satisfies limit x approaching a fx exists and equal to f0 defined. Okay, so for example B, you can try. Okay, so you can try for example B. Okay, when the function undefined, when, of course, when the f0, okay, when not the f0, okay, when the function is equal 0, so x minus 1 equal 0. This function must be undefined. Alright, so we can check whether when the function will be the denominator of the function is 0. So when x plus 3, x minus 2 equal 0. So this is directly, we don't have to use the calculator. So the value of x is negative 3 and 2. Okay, therefore fx has discontinuity. at x equal negative 3 and x equal 2. Okay. Okay, for example C. Okay, for example C is polynomial. So for the polynomial function continuous everywhere. Okay, defined everywhere. The limit exists everywhere. So for the example C, okay, fx continuous everywhere. So everywhere. That means the fx does not has the discontinuity point. So you can try for the example D. Okay, I will give the answer. Let me check. Fx, okay, for the example D, fx also continuous everywhere. I think. Okay, why? Uh, you have to think by yourself. Okay, why? So you need to connect the discontinuity, the condition for the for the continuity, and the point of discontinuity, and so on. Okay, but for D, the function is continuous everywhere. Let me check once again. All right, continuous everywhere. Okay, all right. So for the example 18, find the value for the constant k that makes the function below discontinuous. Okay, discontinuous. So where is k? So k is here. Okay. So for the function is continuous. Okay, for this function is continuous. The limit. This question is the same pattern. That's what the piecewise function is the same pattern with the example 16c. So you can check my solution there. Okay, but uh, this time, okay, we need to find the one constant, okay, that make the function discontinuous. Okay, this is just the same. Okay, if the function is continuous. Okay, the function is continuous. Okay, since the value, okay, the point where the interval, the end of interval point is x equals 0, so we need to check only at x approaching 0. Okay, so x approaching 0, cos x divided by 2 minus 1. Okay, we need to check this. The limit is continuous if the limit is continuous. No, the function is continuous if the limit is equal to, okay, let me rewrite this. Let's say this is fx. Okay, this is continuous if the limit is equal to f0. Okay, the limit is continuous if x for x equal, but discontinuous if the limit does not equal f0. Okay, discontinuous. Atau or does not continue, discontinuous. Okay, so we just substitute when x approaching 0. Our fx now is cos x divided by 2 minus 1. Must not equal to f0. F0 is k plus 3. Okay, since we don't have the variable x here, so this k plus t is constant. So find the limit from for the x approaching 0. So cos 0, 1. 1 over 2 minus 1 over 2. So 1 over 2 not equal to k plus 3. Therefore, k, okay, when the function is discontinuous when k not equal to 1 plus 2 minus 3 over 1 plus 2, 1 over 2, 1 over 2 minus 3, or negative 5 over 2. Okay, I see it. Okay, the function is only continuous if k is negative 5 over 2. Other than that, the function will be discontinuous. Okay. Last one is the example 19. So for the example 19, we just look at the given graph. Okay. From the graph below, at which point are the functions discontinuous? Classify the type of discontinuity. Okay, we look at the first graph first. Okay, for the first graph, if we look at here, okay, so if we look at x negative 1, okay, x negative 1, here we have the point discontinuity here. Okay, the second one, if you have here x equals 0, okay, why? Because of the infinite. Okay, then we have here x equals 0 lah. Also the removable. Okay. Okay, then we check x equal 1 also here. For the other points is okay. So we can write the answer. We want the point or the function discontinuous. Okay, the function is discontinuous at, okay, for the example A, at when x equal negative 1. X equal negative 1, what is the type of the discontinuity? This is the jump discontinuity. Okay. The second point is 0. X equals 0. X equals 0 is infinite discontinuity. Okay. The last one is x equal 1. Okay, for the x equal 1, what is the type of discontinuity? Okay, so here we have the removable discontinuity. And then we need to check for the example B. For the example B, we check one by one. So for the first one is here. Okay, we have like the removable discontinuity here. Okay, then also here, this is the jump discontinuity. Also here, at x equal 1, here, not here, at the point x equal 1, we have the infinite discontinuity. Okay. Okay, So as for the end of graph here, so we not consider because we want to check in between the graph. Okay, in between the interval in the graph. Okay, the first part, the end of interval, uh, we not consider anything. Okay, so for the first one is x equal -2. Okay, the function is discontinuous at x equal -2. X equal -2 is the removable discontinuity. Alright, so next is x equal -1. So x equal -1 is jump discontinuity. The last one is x equal 1. X equal 1 is the infinite discontinuity. Okay. Um, okay. Discontinuity. Okay. For the oscillatory discontinuity, the example is obviously sine, cosine. Okay. Because of the function oscillates. Okay, and not approach any point. Okay. I think this is the last example for the continuity and discontinuity. Yeah. So I will stop here for this example about the continuity. So I hope you can understand how to determine the continuity of a function using the limit condition, limit and the function condition at a certain point, and then you can uh, determine the type of discontinuity if we have the graph or the function, if we sketch the function, and we know how to find the point of the discontinuity using the limit condition. Okay, that's all. Thank you.